So we saw earlier that there could be signals which need not satisfy absolute integrability, but still the Fourier transforms can exist. Now, whenever the signal is absolutely integrable, it is easier to find out the Fourier transform. We can directly use the formula and then compute the Fourier transform. But what if the signal is absolutely not integrable? Then how do we find the Fourier transform? So essentially, there could be cases where the integration could lead to infinity. So can we model such cases using a special case? Is it possible to find the Fourier transform in such cases? The answer is yes. In fact, Dirac delta function once again comes to our rescue here. It tells us there are certain cases where even if the signal is not absolutely integrable, we can still model the spectrum at certain points using Dirac delta signal. So we'll see some examples. So the first example is the most common signal that we saw earlier, the unit step function. The unit step function, like if you turn on the input to a circuit, let's say the input is a battery, DC battery, then the input can be easily modeled using a unit step function, right? So this is how the unit step function looks like. So this is a very commonly encountered signal, and unfortunately this signal is not absolutely integrable. So if the signal is not absolutely integrable, then can we even define Fourier transform? If we cannot define the Fourier transform for the unit step function, then most of the circuits cannot be even analyzed with the Fourier transform, because this is what the standard input to several circuits will be. Just turn on the battery and this would be the input. So thankfully we do have a Fourier transform for the unit step signal. And the way that we compute this Fourier transform is in a very slightly tricky and a complicated manner. I'll show this now. So for the first thing that we are going to do is we are going to write unit step function as a limit of certain exponentials. All we are going to say is, I'll consider a set of exponentials which look like this. Okay, and as the exponent becomes smaller and smaller, then we have a signal which keeps changing, and then eventually for the exponent a equal to 0, so if you substitute a equal to 0 here, we'll just simply get 1, right? So this entire signal now would look like just a unit step function. So what are we going to do is we are now going to consider this as a limit of such set of functions. Okay, so now let's find the Fourier transform of this. So we'll say the Fourier transform of this signal. We'll take the limit outside. We'll say limit a tends to 0, integral minus infinity to infinity, e power minus at u of t, e power minus j omega t dt. This is the Fourier transform, right? So we cannot arbitrarily exchange limits and integrals. So let us assume all the required conditions are satisfied here. Okay, and if this is true, just substitute this property of the unit step function. There's one only between 0 and infinity. So what do we have here? So finally we have e power minus a plus j omega t dt. This is limit a tends to 0, 1 by a plus j omega whole minus e power a plus j omega 0 to infinity. So when you substitute infinity, you get just 0 here, and when you substitute 1, you just get limit a tends to 0. You just get a minus 1 in the top, which is 1 by a plus j omega. Okay, so this is the Fourier transform. So now we have to apply the limits here. So it appears it's easy to apply the limits, but the main problem comes when omega itself is equal to 0. When omega is not equal to 0, then you apply the limits, you will simply get 1 by j omega when omega is not equal to 0. But what happens when omega is equal to 0? Then that is a tricky situation. So in other words, we can rewrite this as limit a tends to infinity 1 by a square plus omega square into A minus j omega. Basically, what have we done? We have multiplied and divided with the conjugate. So you just multiply and divide by the conjugate, then you get whatever we have here. Okay. So if you apply A equals 0, so how will we compute this term? When omega is not equal to 0, what happens to this term? When you substitute A equal to 0, we have 0 by omega square, which is equal to 0. So we don't have an issue. But what if omega is equal to 0? If omega is equal to 0, then we have 0 by 0 form. In other words, which is undeterminate. But what we can do is we can apply L'Hopital. If we apply L'Hopital, what we will get is 1 by 2a, which will go to infinity. So we can now clearly say that this signal will go to infinity, that is this term alone will go to infinity when omega is equal to 0. In all other cases, it goes to 0. In other words, we can say that this is a Dirac delta. But the area of this Dirac delta is always 1. Will this signal have an area of 1? That is something that we have to check. In other words, if we say that y of omega is equal to a by a square plus omega square, is the area under this curve equal to 1? Only then this is true, right? So you compute the area of this curve, which is a by a square plus omega square. So remember, what are we letting here to go to 0? The limit here says the a is going to 0. So we are integrating here with respect to omega, not a. So we are fixing a, and then we are letting the omega go from minus infinity to plus infinity. That gives us the area of this signal. And this is nothing but tan inverse of omega by a from minus infinity to plus infinity. So you get tan inverse of infinity, which is pi by 2, minus tan inverse of minus infinity, which is minus pi by 2. You get pi. So the area is pi. Okay. So because the area is pi, now we computed this area without even plugging in a particular value of a. So for all values of a, this area has to be pi, irrespective of what it is. So that has to be true even here, right? As long as the value of a is positive, it has to be pi. And that should be true even when we apply the limit. But here we are getting an area which is equal to 1 when you integrate from minus infinity to plus infinity over omega. So what is missing here is the scaling factor. So we will say what we are actually having here when a tends to infinity is pi times delta of omega. So we can now find out what this limit is. So this limit is in fact equal to pi times delta of omega. So what happens in this case, when omega not equal to 0, you let a equals 0, we get minus j omega by omega square, which is equal to 1 by j omega. Right? This gets cancelled, minus j, you can bring it down, it becomes plus 1 by j omega. And for this term, we have to ensure that omega is not equal to 0. And when omega equal to 0, what do we have? When omega is equal to 0, we directly have 0 divided by a square plus 0. So this term is already 0. So this is 0 whenever omega is equal to 0. So because we have an omega at the numerator, it is taken care and we don't have an undefined form. So this is what we get as the Fourier transform of the unit step function. The unit step function looks so simple, but the spectrum is not so easy to compute. The spectrum looks like this. Now if you try and plot the spectrum of the unit step function, there is an impulse at 0 and the area is pi. So this is the spectrum of, and what happens at all other points? At all other points we have 1 by omega. So one thing to note is, this looks like a low pass filter. So it increases the amplitude of lower frequencies because the amplitude, the gain or the frequency response for lower frequencies is very high, and at frequencies go down, the frequency response is almost closer to 0, which means it vanishes and attenuates those frequencies. So this is very similar to a low pass filter, an approximate low pass filter, right? So which means if I have a signal and I convolve with it with u of t, what is that we are actually doing? We are basically taking this integration. This operation essentially is a low pass filter. So the integration is a low pass filter. So we can get this insight. See, the entire task that we were doing so far seemed so complicated. But what is the result of this complication? The result of this complication is a nice insight that the integration task, which is basically convolution with a unit step function, behaves like a low pass filter. So if you want a low pass filter in real life, and if you are okay with approximating it in this form, then you can simply use an integrator. An integrator is a substitute for a low pass filter. Okay, from this we can also find out the Fourier transform of several other signals. For example, if you want to find out the Fourier transform of a constant, let us say x of t is equal to c, then what is the Fourier transform? You can write this as c of u of t plus u of minus t, correct? So now take Fourier transforms on both sides. Applying Fourier transform on both sides, you get f of x of t is equal to c times the Fourier transform of u of t. The Fourier transform of u of t is what? The Fourier transform of u of t is whatever we derived here, that is pi of delta of omega plus 1 by j omega. What is the Fourier transform of u of minus t? Now we use the properties of Fourier transform. When there is a time reversal, there is a reversal in frequency also. So you get minus omega plus minus j omega. These two get cancelled. So we are left out with 2 pi delta of omega plus c, because delta is an even signal. So this is what we get as the Fourier transform of a constant. So this is so simple. Directly by knowing this relationship, we can find out the Fourier transform of the constant. Earlier, remember, we said the integration of minus infinity to plus infinity e power j omega t dt is equal to 2 pi delta of omega. Do you know where this came from? This is where it came from. So when there is a constant, so if there is a constant c, what is its Fourier transform? E power minus j omega t dt, right? And now we are saying this is equal to 2 pi delta of omega c. And if c is 1, then you get this relationship. So from this relationship, we can say that this relationship is something that we have been using so far many times. But how did we get to this relationship? This is because of this Fourier transform properties. Okay, so clearly this tells us that the Fourier transform of a constant is nothing but an impulse, and this makes sense, right? So why does this make sense? So let us try and plot the spectrum. So if we plot the spectrum, how does this look like? It looks like an impulse, and the area of this impulse is 2 pi c. And it makes sense because a constant is basically a DC signal. It has no other frequency components, nothing else. It is just a DC signal, which means the spectrum should also reflect that at omega equal to 0, that is frequency is equal to 0, we should see some non-zero values. For everything else, we should see 0. That's exactly what we are seeing here. We are seeing a non-zero spectrum only for the DC value, everywhere else it is 0. We can also find out the Fourier transform of other interesting signals. For example, what if you want to find out the Fourier transform of the Signum function? So what is the Signum function? The Signum function is +1 for all positive values and it is -1 for all negative values. In other words, we will say that sine of t is equal to +1 for t greater than 0, -1 for t less than 0. So if you plot it, it looks like this. This is 0, this is t, this is +1, this is minus. This is the sine of function. So the nice thing that we can do is, instead of doing all the integration, we can write this as u of t minus u of minus t. Life is simple if you can just express this as the unit step function. Now apply Fourier transform on both sides, then Fourier transform tells you that this is pi of delta of omega plus 1 by j omega minus pi of delta of minus omega minus 1 by minus j omega. So these two get cancelled because delta is an even signal, and these two get added up. So you get 2 by j omega. So a Signum function also behaves like a low pass filter. Not only is the unit step function a low pass filter, but the Signum function is also a low pass filter. But we do not use Signum function simply because, of course, it is not causal. There is non-zero values for the negative values of time also. So Signum function, even though it is a low pass filter, it is non-causal. So we don't bother about that in real life. Now let's see what happens to the Fourier transform of the differentiator and the integrator. Okay. So now it's once again very similar to what we saw in the Fourier series case. It's very simple also. So if we have the Fourier transform of the derivative of some x of t, what is the corresponding relationship between the Fourier transform of the original signal? So the Fourier transform of d by dt x of t e power minus j omega t dt. So we can say that x of t is equal to 1 by 2 pi integral minus infinity to infinity x of j omega e power j omega t d omega. Now take the derivative. If you take the derivative, you have 1 by 2 pi. Now we'll take the derivative inside, because this integration is anyway only in terms of omega, but the derivative is in terms of t, so we can take the derivative inside. If you take the derivative inside, you get d by dt of this phasor, because the t term exists only here. If you take the derivative, you get j omega times e power j omega t, which is as good as saying that if this is some y of t, then 1 by 2 pi, let us call this y of j omega, then you have y of j omega e power j omega t d omega. So this is the inverse Fourier transform, implies the Fourier transform of the derivative is j omega times x of j omega. So we have this relationship where when you take the derivative, the Fourier transforms are just multiplied with j omega. In other words, this is the frequency response of the derivative operator. So if you have a differentiator, then the frequency response of the differentiator is simply j omega, and we saw that this behaves like a high pass filter. Okay, so basically it has, if you try to compute mod j omega, it looks like this, right? It behaves like approximately like a high pass filter, not a good high pass filter, but approximately like an high pass filter. So same as in Fourier series case, even here we have the same reaction to the differentiation operation. So this is also apparent from our eigenvalue eigenfunction understanding, right? So the complex sinusoid or the phasor behaves exactly like eigenfunction to the derivative operation. So when you compute the Fourier transform, what are you trying to do here? We are just expressing all these time domain signal as some scaled version of the complex phasors or the complex sinusoids, and anyway they are the eigenfunctions, which means all they'll do is get scaled by some amount, that's all, and that eigenvalue we know is j omega, and that's exactly what is happening here. Whatever is the input, it just gets scaled with the eigenvalue. Okay, and we can do the same operation for the integration. So in fact, we can simplify this. If x of t, let us say y of t is the integral of x of t, then we can write this as convolution of x of t with u of t. And we'll use this property now. Then what is the Fourier transform of y of t? It is the product of these two. And we already know what is the Fourier transform of u of j omega. We just derived it. The Fourier transform of the unit step function is pi Dirac delta omega plus 1 by j omega. All you have to do is just simply multiply that. So when you multiply these two, what do you get? You get pi. And this term, you know what happens when you multiply with the Dirac delta. So only the value at 0 matters. Everywhere else it anyway gets multiplied with 0, so it's just 0 plus x of j omega plus by j omega, x of j omega by j omega. So this is the output of the integrator. So once again, what does it say? It says that the DC frequency is kept as such, because whenever there is a DC component, you retain it as such. But if the input does not have any DC, then the output also does not have any DC. So the DC is just scale with pi, and then you don't change anything to the DC. But what happens to the other frequencies? The higher the frequency, lower is their gain. So if omega is, let's say, 10 power 4, then the frequency response is, in this case, 10 power minus 4. It gets multiplied with 10 power minus 4. So the higher frequencies are attenuated a lot. So this is like a low pass filter, whereas a differentiator is a high pass filter. So whatever that we saw in Fourier series directly holds for the Fourier transform. The integrator behaves slightly differently, because in the case of Fourier series, we just simply saw that the frequency response is just 1 by j omega. You multiply with that and you are happy. But in Fourier transform, because the integrator is not absolutely integrable, we take care of that by multiplying with the Dirac delta signal. Okay, and that has to appear here. So to ensure that you get the DC component, because this term exists only when omega is not equal to 0, and this term takes care of what happens when omega is equal to 0. So it is slightly different now. The differentiator was exactly the same in the Fourier series, but the integrator is slightly different. So this you have to keep in mind.